Hi, welcome to our tutorial entitled A Unified Framework for Underdetermined and Determined Blind Audio Source Separation. My name is Nobutaka Ito. I'm gonna present the second half of section 1 and sections 4 to 8.
Hello everyone, my name is Hiroshi Sawada. I'm presenting the first half of section 1 and section 2 and section 3. Section 1, Introduction. This tutorial is about blind source separation, or BSS for short, for audio signals, which aims to separate original source signals from their mixtures. Let me start with the application of BSS. We humans can focus on a particular person's speech, even at a noisy cocktail party. This is called a cocktail party effect. Realizing this by a computer is an application of BSS. Another application is automatic speech recognition in a noisy or meeting situation. The performance of automatic speech recognition degrades severely in the presence of simultaneous speakers or background noise. BSS makes accurate automatic speech recognition possible even in such a situation. Other applications of BSS include music analysis. To give the audience an idea of what is BSS, we plan to perform a live BSS demonstration during this tutorial if we could get together in a room. However, EUSIPCO 2020 has become a virtual conference because of the COVID-19 pandemic. So instead, we recorded some speech mixtures on our own. The recording situation will be shown soon, and the recorded speech mixtures will be separated by the method explained in this tutorial. In a live demonstration, we are going to separate 2 or 3 speakers' voices recorded by using 2 microphones on an IC recorder. We usually ask for some volunteers as speakers. We have prepared some scripts so that the volunteers have something to speak. Now we are switching to the recording situation where 2 speeches are mixed. Hi, from now we are going to record speech mixtures with this IC recorder equipped with 2 microphones. Here and here. So let's start. 3, 2, 1.
We are demonstrating blind source separation for convoluted mixtures of speech in a real room with real talkers.
Thank you. Now we are coming back from the recording situation. BSS aims to separate original source signals from their mixtures. For example, in this figure, 2 persons are speaking at the same time, and this situation is recorded by 2 microphones. What are recorded by the microphones are the mixtures of the speech signals of these speakers. BSS processes the mixtures at the microphones X1 and X2 and produces the output signals Y0 and Y2, which are ideally equal to the original source signals S1 and S2. However, in this scenario, the information about the source activity and the mixing system denoted by A is assumed to be unknown, which is why it is said to be blind. In the simplest case, the mixing system A is described by scalars, and sources are multiplied by the scalars and then mixed. This is called instantaneous BSS and regarded as a basic BSS model. However, in a real-room situation, we have delays between the mouth and the microphones, and also reverberations from the walls and the floor. So, the mixing system A is described by impulse responses, and sources are convolutively mixed. This is called convolutive BSS. This is a much harder problem than instantaneous BSS, but in this tutorial we discuss this type of BSS problem. Most methods for convolutive BSS operate in the time-frequency domain using the short-time Fourier transform, STFT. By applying STFT to a time domain signal, we have time-frequency domain signal whose amplitude representation is called spectrogram. What is nice about STFT is to make it possible to approximate the convoluted mixtures by instantaneous mixtures in each frequency bin, thereby simplifying the problem in some way. In the frequency domain, complex-valued signals are processed, and we have frequency bin axis indexed by I and time frame axis indexed by J. And together with the multi-channel setting we are working on, we have tensor representation with three axes: frequency, time, and channel. This slide summarizes the notations we are going to use in this tutorial. One crucial distinction in the BSS problems is determined or underdetermined. Determined BSS is for a situation where the number of sources is equal to or less than the number of microphones. This is regarded as a basic BSS problem, but the applications might be limited because many microphones are required to separate many sources. Underdetermined BSS is for a situation where the number of sources is greater than the number of microphones. This has wide applications because we can separate many sources, for example, with only 2 microphones. But this is a very challenging problem. This slide shows the scope of this tutorial. We will cover multi-channel settings with determined and underdetermined situations. We will not cover a single channel setting. Also, we will not cover DNN-based methods that can take advantage of learning source characteristics beforehand by utilizing training data. Now we are switching to the recording situation where 3 speeches are mixed. Please note that the previous video was for determined BSS, but this time, because the number of sources are 3, this is underdetermined BSS. Next, we are going to record 3 persons speech mixtures. 2, 1.
We are demonstrating rhymes of operation for cognitive mixtures of speech in real rooms with real talkers.
Now we are coming back from the recording situation.
In this tutorial, we introduce 8 BSS methods listed here, which consist of 2 determined BSS methods and 6 underdetermined BSS methods. Furthermore, we elucidate close theoretical connections among these 8 methods. As shown in this figure, these connections are represented by a cube. The 8 vertices represent the 8 methods. The 3 axes correspond to 3 constraints imposed on model parameters. Here we call this a unified framework. This slide shows the structure of this tutorial. We are now in Section 1, Introduction. In Sections 2 and 3, we treat determined BSS methods. Time-varying Gaussian ICA is explained in Section 2. ILRMA is explained in Section 3. In Sections 4 to 7, we treat underdetermined BSS methods. R1CA is introduced in Section 4, FCA in Section 5, and FastFCA in Section 6. In Section 7, we introduce Rank 1 MNMF, Full Rank MNMF, and FastMNMF. Finally, the 3 constraints corresponding to the 3 axes are explained in Section 8.
Section 2, Time-varying Gaussian ICA, Independent Component Analysis. In this picture of the tutorial structure, this section is located here, colored in yellow, and it is in the determined BSS methods, colored in green. If we zoom into the determined BSS, we have time-varying Gaussian ICA explained in this section, and also ILRMA presented in the next section. The distinction between these two is narrowband or full band. In the narrowband model, separation procedures are performed separately in each frequency bin. In this figure, this is shown in different colors. So, in this section regarding narrowband model, we will usually omit frequency index I. The topic of this section is ICA, independent component analysis. ICA has been studied for more than 30 years, and there have been proposed many source models as well as many algorithms. Among them, in this tutorial, we are especially interested in time-varying Gaussian ICA. The reason for selecting this specific ICA model is because it is suitable for the extensions to full-band cases and also underdetermined cases, both of which will be explained in the following sections. This slide shows the basic idea of ICA. What we want to do is to extract the original sources, two-person voice in this case, from the mixtures X. However, the information about mixing matrix A is not given a priori. If the two persons picks different contents on their own pace, the two persons' voice can be assumed to be independent of each other. So, if we design the separation matrix W to make the output Y independent of each other, we might be able to recover the sources. In addition to independence, we need to assume further that the source distributions are different from Gaussian. And we want to make the distributions of the output Y far from Gaussian. If the sources are Gaussian, all we can do is to decorrelate the mixtures, and the decorrelation is not the same as the separation. So the source model is crucial in ICA and should be different from Gaussian. Since we are working in the frequency domain, source signals are complex valued. For audio or speech sources, we model them as super Gaussian distributions. A well-established way is to employ this distribution, which is like Laplace distribution, and parameterized with a smoothing parameter alpha. However, in this tutorial, we employ time-varying Gaussian distributions. What is time-varying is the variance of the Gaussian distribution. So the variance depends on time, which is indexed by J. It is known that time-varying Gaussian is super Gaussian overall, so it can be regarded as a valid source model for ICA. Please note that time-varying Gaussian is different from time-invariant Gaussian, which leads to only decorrelation. This slide shows the difference between time-invariant Gaussian and time-variant Gaussian. Time-invariant Gaussian, which we have recognized as an ordinary Gaussian distribution, has a fixed variance, and samples are generated as shown in this figure. On the other hand, time-varying Gaussian, which we are going to employ in this tutorial, has a time-varying variance, and each time sample is generated based on the time-dependent specific distribution. This slide shows an example of a source signal generated from time-varying Gaussian distributions. We made the signal real-valued for simpler visualization. On the left, we have time-varying variances for every time frame j. And on the right, we have generated source signal samples. As you can see in the samples on the right, we have basically many zeros and sometimes larger values. This is one of the characteristics of a super Gaussian distribution. This slide shows the total ICA model, in which we have 4 assumptions. The first one is linear operation. Separated signal Y should be made by a linear operation W to the mixtures X. The probability density functions of X and Y are related by the determinant of W. The second one is output independence. We would like to make Y to be independent of each other. The third one is sample independence, which makes the parameter estimation easy. The fourth one is non-Gaussianity, which we have just discussed in the previous 3 slides. In this slide, we will define ICA cost function. We take the maximum likelihood approach and want to minimize the negative log likelihood function. By putting all the equations of the previous slide together, we have this form for the negative log likelihood function. Then we define a so-called contrast function G that reflects the ICA source model. Finally, we obtain the ICA cost function in a general form, which consists of the contrast function G and the log determinant term of the separation matrix W. We employ time-varying Gaussian whose probability density function is of this form. So the contrast function G is of this form. By putting the contrast function into the general ICA cost function, we have a specific ICA cost function of this form. This specific function form can effectively be minimized by the algorithm explained in the next 4 slides. First, we consider the minimization of the cost function by optimizing the variance parameter h. By calculating the derivative of the cost function with respect to h and setting the derivative to 0, we have this simple equation. In practice, to avoid a very small number for h, we do flooring by adding a hyperparameter alpha, for example, 0.01. Then we consider the minimization of the cost function by optimizing the separation matrix W. Let me rewrite the cost function by making W explicit and then by introducing a weighted covariance matrix Q defined here. So this is the cost function rewritten. By calculating the derivative of the cost function with respect to W and setting the derivative to a Dale matrix, we have these equations in which this is the Kronecker delta. For example, if n is equal to 3, we have 9 equations shown here. The separation matrix W is optimized by solving the simultaneous equations. This problem is called HEAD, Hybrid Exact Approximate Diagonalization. It is equivalent to a generalized eigenvalue problem when n is equal to 2. However, no closed-form solution has ever been found when n is equal to 3 or larger than 3. A method called iterative projection, IP, is getting its popularity to solve the HEAD problem. It is basically a block coordinate descent method, and one column of W is updated at a time instead of the whole matrix. The actual operation for updating a column is by these two steps, which are like solving these three simultaneous equations when the target column is W1. In summary, this slide shows the whole algorithm for time-varying Gaussian ICA. We iterate the 4 types of operations until convergence. The first one is separated signal calculation. This is essential for ICA. The second one is to update the variance parameters with the power of separated signals. The third one is to update the weighted covariance matrices with the variance parameters just updated. The fourth one is to update the separation matrix by iterative projection IP. The update is performed sequentially for each source n based on the weighted covariance matrix calculated for each source n. We implemented a Python code for time-varying ICA and an IPython notebook code for generating synthetic data and also for visualizations. In this case, we generated 2 real-valued sources and mixed with this mixing matrix. The ICA algorithm starts from here, and with 10 iterations, the sources are well separated. The upper right figure shows how the cost function is minimized as the iteration goes on. We see a first convergence here. This is the IPython notebook code for executing time-varying Gaussian ICA. First, we import NumPy and matplotlib, and also our own code implementing time-varying Gaussian ICA. The Python code, ICA Python code, is like this. It's just 50 lines of code. Then we define a function to generate a source based on time-varying Gaussian. For time-varying variances, we used gamma distribution here. Now we generate one source signal here. And let me plot the variance and also the generated sources here. Then I generate 2 sources here. So this is the plot of two sources, and on the right we have scattered plot for source 1 on the x-axis and source 2 for the y-axis. This kind of shape of plot indicates that the two sources are independent of each other, and also they are super Gaussian. Then I mix the sources with this mixing matrix. This is the plot of mixed signals, and on the right we have scatter plot for the mixture x1 on the x-axis and x2 on the y-axis. Apparently, these two signals are correlated. Then I perform ICA, time-varying ICA, just implemented like this. Then once it is converged, we can get separated signal Y here. Let me see the separated signal by plotting them. And on the right, we can see that Y1 and Y2 are well separated from this shape of the plot. This plot shows the convergence. We just executed 20 iterations, and the cost function is well minimized. This is the plot of how the separated signal Y changes from the beginning to the 10th iteration. We can see that the separated signal is well separated at the very early stage of the iteration. This is the last slide of this section, time-varying Gaussian ICA, and summarizes the key concepts introduced in this section and should be carried over to the next sections. The first one is time-varying Gaussian source model, parameterized with time-varying variances. The second one is the algorithm with iterative projection, IP, by which a cost function of this form can effectively be minimized. Similar function forms will appear in this tutorial. This is the end of section 2.